Welcome back to our series on projectile motion. Let's review a few things so that we can continue to comprehend how to decompose X and Y components in two-dimensional projectile motion analysis. We remember from our previous lessons that two-dimensional motion consists of vectors along the x-axis and vertically along the y-axis. And we need to be able to discover a few elements within each of these in order to solve some problems in the real world. One of the first things we're going to notice are things along the x direction. One thing we're going to want to know all the time is what is our velocity of a projectile in this horizontal x direction. And the equation for that is that the velocity of x at any given time is equal to Vx naught. Vx naught simply means the initial velocity. We could actually say Vi, and some people use that term. And it's going to continue to be that velocity the entire time. There's nothing that actually slows down something moving along the x-axis except for air friction, or inevitably someone's going to catch a ball and stop it, or it'll fall to the earth because of the y forces of gravity. But for calculation purposes, the vector along the x-axis, the x component, is always going to be whatever it was at the beginning. The position of a projectile along the x-axis can be calculated with this following equation. The position x equals Vx naught, which is the velocity that it was launched at, times the amount of time that we're looking at the position. In other words, at 1 second, 2 seconds, or 3 seconds, the position is going to be somewhere along that line, and it's going to be at that point of seconds times the meters per second that it was launched. Now, sometimes we have to imagine in our mind that we have a projection of the cosine angle onto the x, but inevitably it still equals 1. Along the y direction, we find these equations. The velocity always equals the velocity that it was launched or thrown at, minus the effect of the acceleration of gravity times time at any given moment along the y-axis. Gravity being 9.8 meters per second squared. So our velocity at any given time on the y component is going to be the velocity at which it had started minus the effect of gravity over a certain period of time at which we want to look at it. This is going to help us find out a lot of answers also. The position of y at any given moment of time follows this dynamic. Vy naught, which is basically the velocity at which it was launched on the y component, times the amount of time that we're looking at, minus 1/2 the force of gravity times time squared. We also see that we have an equation similar to what we found in our first part for one-dimensional position and velocity, in that velocity in the y component direction squared is going to equal the velocity y naught squared minus 2 times the force of gravity times the position of y. These help us calculate a variety of problems that we're going to find out in our next section. Now, I have gone ahead and saved these equations on the board for us to work with. But a lot of this seems a bit like gobbledygook, and you think to yourself, well, what good is this going to be for me? Well, let's go out in the real world and see if we can find something in which we can use these to figure out something of interest. Come on. Okay, great. Now that we've finished our review of motion calculations in one direction, either along the x-axis in the horizontal direction or along the y-axis vertically, it's time to incorporate in two dimensions at the same time. This has many great applications, such as sending a rocket to the moon or firing artillery shells and making sure they're on target. But we don't have any rockets, and we don't have any big guns. So one of the best ways to study projectile motion in 2 dimensions is to take a look at the good old American softball. Now let's review a couple of simple rules about our motion in both the X and the Y direction. For the purposes of calculation, it's important to remember that in the theory of mathematical measurement, the movement in the X direction doesn't have anything that slows it down or stops it. That is to say that once we start moving this ball in a certain direction, if it wasn't for the fact that it's getting caught by somebody or that it finally falls to the earth and stops because of gravity, well, if you discount the gravity, that ball would always move in that direction for as far as it could go. That's an important thing to remember because our initial velocity is important in our calculations on the x-axis. Now, when we're going to incorporate the y-axis with the motion of the x-axis so that both of those components can be measured and the trajectories of the path, the vector, be calculated properly, it's important to understand that the entire time that we have motion in the y direction, the force of gravity is pulling it back down to earth. And we know that force of gravity is an acceleration of 9.8 meters per second squared. So, when we combine the x component and the y component properly, using our calculations of motion and projectile measurement, we can begin to analyze projectile motion properly. So just how do we incorporate both the x-axis energy and the y-axis energy with our calculations to predict the flight of our projectile? Let's head back to the drawing board for a look. Well, okay. I think that just using a softball is a great way to understand projectile motion. We've got the effects of gravity on the straight up and down y vector, and we have a component of the horizontal vector. So let's really start with the fundamentals. Why don't we just deal with the vertical ball toss? We'll go ahead and plot this out. And what we'll do is we'll just simply toss a ball straight up into the air, let it come back down, and we'll try and find out what that time is from the time it's launched to the time it comes back down. You'll be amazed at how much we can find out from something this simple. By beginning with a vertical ball toss, we'll be able to address the forces along the y-axis with simply the displacement of the ball along that axis and the amount of time it's in the air. Let's take a look. Okay, we've done the actual experiment and we've timed the ball toss straight up into the air. What did we find? Well, we found that the time of the ball toss from when he threw it in the air to when he caught it equaled 3.0 seconds. Well, what can we do with that? Now that we know that the time for the entire ball toss was 3 seconds, we have to kind of look at this and assume something. If the ball goes up to the top of its apex and then turns around and comes back down because of the force of gravity, we need to assume then that from the initial toss to the point at the top is 1.5 seconds. And, well, that's going up. And we have to assume then that going back down is 1.5 seconds also. This is actually kind of important when you think about what we have for equations to work with and what we can find from those equations. The equation that we should use, now that we know a couple of things, is going to be this one right here. The velocity of y equals the velocity of y naught minus gravity times time. Because now we have time, we know what gravity is, we just don't know what the velocity is when we threw the ball. However, we do know what the velocity is when it reaches the apex. Because once it goes up to the top, it stops under the force of gravity and comes back down. So at the top of its apex, the velocity is 0. What can we do with that? Well, it's simple. If we put this into our equation, we will find that Vy equals Vy naught minus gravity times time. Well, it's just plug and chug. Vy is going to equal 0 minus the force of gravity times time, which we've determined is 1.5 seconds. If we go ahead and figure this out, we will find that Vy is going to equal 14.7 meters per second. That's the velocity of, well, actually it's minus 14.7 meters per second because it's moving down. So at the time that our ball tosser caught the ball, the velocity was a negative 14.7 meters per second. Now, this is going to turn out to be a little bit important in the second half of what we may want to do, because what we want to find out then is that what was the velocity at V naught? Well, if the velocity was 14.7 meters per second down, being negative when he caught it, it stands to reason then that the velocity when he threw it is a positive 14.7 meters per second. Now, let's see what we can do with that. We'll take a look at perhaps finding out just how high the ball traveled when we threw it up. Because we might want to find out some other information or pose a different problem in the second half of our experiment. Remember that the position of y, which is basically the height that we want to find out, y equals the velocity of y naught times the amount of time that it's going minus 1/2 the force of gravity times the time that it's going squared. And we know that the ball was thrown upwards at 14.7 meters per second. So, all we need to do is plug and chug with our calculation equation that we have here. We have 14.7 times 1.5 seconds minus 1/2 times 9.8 times the 1.5 seconds squared. If we do all that math, we basically end up getting 11.03 meters. And if you'd like to go ahead and convert that to feet, because we are in America and softball's kind of figured in feet, we remember that there's 3.28 feet for every meter. And if you do the calculation conversion there, we'll find that the ball was thrown a little bit over 36 feet high, 36.18 feet. So now, using just a couple of equations and manipulating the facts that we found just by timing a ball toss in the air and knowing the force of gravity, we know that a ball was tossed at a velocity of 14.7 meters per second, and we know that it was sent to a height of about 36 feet. Now let's see what happens if we combine an X component and a Y component by throwing the ball at an angle rather than just straight up and down. Now we've determined some very important information from just the ball's travels along the y-axis. But let's pose a simple problem that incorporates both vectors of the x-axis and the y-axis. Let's say that the hover here now needs to throw the ball home, and she needs it to be a certain height in order for it to completely be there. So let's make this the problem. If Aubrey throws the ball at a 50-degree angle, what velocity would she have to throw it to reach the same height that we found our vertical toss made it to? The second half of our problem is posed as such. We're going to have little Aubrey throw the softball at a 50-degree angle to reach the same height as the vertical ball toss. And what we want to know is how fast she has to throw that ball to reach the same height at 50 degrees. And the way we need to work that out is pretty simple. We know that the velocity times the sine of 50 degrees has to equal 14.7 meters per second. That is, the projection of the sine on the y component times the velocity is going to equal the same velocity we had when it was strictly up and down. So we take the velocity times the sine, which is 0.766, and that has to equal 14.7. Divide both by 0.766, and what we get is that V naught is going to equal 19.2 meters per second. So, little Aubrey, to reach the same height as the man that tossed the ball vertically, throwing the ball at 50 degrees, has to launch that ball at 19.2 meters per second. Pretty interesting stuff. But let's check our work and see if that's correct. And one thing I want to do before we check our work is to just go ahead and put all these units into meters so that when we're checking our work we don't make any mistakes. So we said that little Aubrey has to throw the ball at 19.2 meters per second to reach 11 meters high, which is equivalent to that of the ball toss. And so what we're looking for is the position of the ball on the y vector. And we have an equation for that right here. The position of y is going to equal v naught y times the amount of time minus 1/2 the force of gravity times the time that it's there squared. And we just need to plug and chug some of the numbers into this equation to make it happen. So let's do that. V naught, we've discovered, is 19.2 meters per second. And we're looking at it being in the air the same amount of time because it's just the y component of 1.5 seconds. And we're going to minus 1/2 of gravity, which is 9.8 meters per second squared, times the amount of time, which is the 1.5 seconds that we had going up to the apex of what is essentially a parabola, squared. And we want to find out what that's all going to equal. And when you end up doing the math, we find that this is 22.05, and this ends up being 11.02, which equals 11.03 meters, which is the same as this here. And so we verified that the calculation of our equations match and that our experiment was a valid confirmation of our vector projection motion equations. Okay, well, we were able to discover some important information from just a vertical ball toss along the y-axis. And we were able to use some of that information to solve the second half of our problem to find out the velocity that little Aubrey had to throw the ball at 50 degrees to reach the same height. this is one small example of how we can use vector calculations to calculate properly projectile motion in 2 dimensions. In the second half of our series here, we're going to look at some really exciting stuff. I look forward to seeing you then.